here are some reminders of what happened last time. I defined this abstract thing, which is I have a group acting on a plane, preserving two transverse foliations, which can be generalized to ones with isolated prong singularities if you like, but I will ignore that for today. A group is Anosov-like if you have this kind of hyperbolic behavior along leaves that are fixed by elements. You see that everywhere, and when you see branching in the leaf space, there's some element that fixes each leaf that happens to be non-separated with some other. So that's the definition. All of these properties are satisfied by the action on the orbit space that comes from Anosov flows on three manifolds. And so you can study these as interesting classes of dynamical systems, but you can also use this as an approach to prove things about Anosov flows. So where did this definition come from? A clunkier version of it, it's still evolving, was what Thomas, Barthelmé, and I came up with as an approach to studying Anosov flows. So what we proved in using this in a joint paper, in two parts, one of us and one joint also with Stephen Frankel, is using this kind of axiomatic approach, we proved the following statement about Anosov flows. Oops, it's good. Which is, so sample application using Anosov-like actions perspective. We proved the following sort of invariant for Anosov flows. Here's a special case. So this is with Thomas Barthelmé. And then also part with Stephen Frankel. It says that if you want to understand Anosov flows, essentially all you need to understand, at least for transitive flows, or if you restrict the manifold a bit, you just need to understand the three homotopy classes of periodic orbits. So precisely, let me state an easy version. Suppose M is atoroidal, or say a hyperbolic three-manifold in the geometric sense. Two Anosov flows, or I can even say pseudo-Anosov, flows on M are the same to a topologist, meaning are equivalent up to time change and conjugacy. So I have the right to rescale time and to change coordinates on M. Actually, let me say conjugacy by some homeomorphism that's isotopic to the identity. So these are really looking the same. If and only if the exact same loops in M are represented by periodic orbits of each flow. So the set of free homotopy classes of unoriented loops, so that's an element of pi1 of M up to conjugacy. So that gamma, maybe, or gamma inverse orientation I don't care about, is a periodic orbit of phi. That's just as a set, not counting multiplicity. This is the same set as the same thing for psi. So this gives you a complete invariant for flows. If you remove hyperbolic, you have to say some extra things that I don't want to get into the weeds about, but we still have a complete invariant. And the way we proved this was to translate this into a statement about groups acting on the plane. Periodic orbits here correspond to fixed points, and you just play with these axioms, and well, 40 pages later, you have this new invariant to classify Anosov flows. So that's a new theorem, but that's not what I'm going to do today. I'm going to reprove an old theorem instead. All right. Our goal today is to prove the following theorem about the structure of foliations associated to Anosov flows. But I will prove it about actually the structure of foliations associated to Anosov-like group actions. Okay. So the flows version of this theorem is due to Thierry Barbot and Sergio Fenley in the 1990s. I'm sort of combining two theorems here, which is why I'm not giving super precise dates. And the actions version is the following. So suppose that I have a group and I have a plane with two transverse foliations, and this is an Anosov-like action. So you preserve the foliations and satisfy all of that kind of stuff. Then actually, there's very strong constraints on what this foliated plane can possibly be. Either P, the plane with its foliations, is the trivial plane as a foliated plane. So that means it's R2 with the product foliations. R cross R is the foliated space. Or P is the example that we see for geodesic flow. So this is isomorphic to the geodesic flow orbit space, which as a foliated plane, one way to draw it concisely is you take an infinite diagonal strip and you put the horizontal vertical foliation on it. Come chat with me at lunch if you want to see why this is geodesic flow and you haven't worked it out yourself. It's nice. Or both foliations have two-sided branching. Okay, what does this mean, two-sided branching? So if I have a foliation of the plane, its leaf space is some possibly non-Hausdorff simply connected one manifold. It's simply connected though, so I can orient it, right? And so I can think of, according to the orientation, when do I have interval of leaves that has, a non-Hausdorff limit. It limits onto at least 2 points. Or when do I have an oriented sequence that does this? Versus when do I have one in the opposite direction that has multiple limit points? Okay, so in the I guess it's connected, right? So it's like there's something weird going on in between. In the foliations case, this is exactly the situation where I see, some leaves that are limited on by a sequence of leaves, and then also somewhere else in the plane going in the opposite sort of transversely oriented direction, I also see a sequence that has multiple limit points. All right. So that's two-sided branching. Okay. So that's what I want to do, is give a different proof. I'm going to give a proof that has some similarity, but is in fact structurally quite different to the Barbot and Fenley proof, using these axioms and organized a bit differently. Yes?
So for the geodesic flow,
yep.
The foliation, if you forget the action, is the same as the top one, right? So the point is that you pick it.
It's not. No? So here, if I take a leaf, it intersects every leaf of the other foliation.
Right.
Yeah, this is the test. All right, here if I take a leaf, it does not. Yeah. So these are not isomorphic as bifoliated planes, even forgetting that action. There are lots of things that are not, there are lots of Anosov flows that are not geodesic float. There are many Anosov flows on even hyperbolic three manifolds, say not things that look like a unit tangent bundle, that have this as their orbit space. Actually, with Jonathan Bowden, we proved that you give me a number, like 100,000, we can build you a hyperbolic three manifold with 100,000 inequivalent in this sense, even if I say allow you to have things that are not isotopic to the identity, really inequivalent Anosov flows, all of whom have this orbit space. All right, so the orbit space doesn't really determine the flow. You need the action, or you need to like record a bunch of data like here. All right. Okay. That's our plan to prove this theorem. I'm going to remind us some vocabulary we had last time, right? This is something about the structure of foliations in a plane. And last time I pointed out one structural feature called lozenge, which is a shape that looks like this. So it's a trivially foliated region bounded by 4 leaves, 2 of each foliation. And so the inside is an open rectangle that with its product foliation. And at 2 opposite corners, it's bounded by leaves that intersect. And the other 2 corners, it's bounded by leaves that do not intersect, but what I called yesterday making a perfect fit. So the interior of this is called a lozenge, and the bounding leaves we call the sides. Okay. This is sort of a natural thing to study just from bifoliated plane perspective because it's a basic object that pops out sort of as soon as you have leaves that don't intersect other leaves. This is kind of like a limiting case of almost intersecting. But it's also very natural from the flows perspective. If you're a 3 manifolds flows person, if you have, let's say it this way, each lozenge in the orbit space comes from taking a Birkhoff annulus in your 3 manifold, if you know what this means, lifting it up to the universal cover and then projecting this to the orbit space. More generally, if you take so each lozenge arises from a Birkhoff annulus picture, and more generally, if you take a random Birkhoff annulus and you do this and you project it, you might not just get a single lozenge, you might get its projection might be a line or even one that kind of starts going on a zigzag like this. But unions of lozenges stacked together are exactly the way to translate back and forth between those and Birkhoff annuli. All right, I'm not defining Birkhoff annulus for anyone who doesn't know what this is already. That was my side remark for people who like flows. Come ask after if you want. Today I want to stay in the plane. All right, so these come, actually here I'll draw you a picture of what a Birkhoff annulus is. Okay, because I feel bad. A Birkhoff annulus is just, it's an annulus that's it's a closed annulus where the interior of it, the non-boundary things, is transverse to the flow, and the boundary is 2 periodic orbits. So you have an annulus that, I never draw it like this, where these are orbits. And the interior of it is transverse. Okay. Other questions? Let's prove a theorem. Yes, question? Yeah?
You say that you need the orbits crossing the annulus will go to the lozenge, or is it?
Yes. So if I lift this to the universal cover, I get 2 periodic orbits, 2 lines that came from the periodic orbits. These, in this case, correspond to these corners. So, sorry, every lozenge that is fixed by some non-trivial element of your fundamental group comes from a Birkhoff annulus. And what happens is you have your annulus lifted to the universal cover. It has its 2 periodic orbits. And inside, this represents squares worth of orbits. A fundamental domain is going to look something like this. And the action of G, representing the fundamental group of this, is going to translate this fundamental domain over. In G and G inverse in both directions. No. Cool. Other questions? Okay. Okay. To prove this theorem, I need a lemma. Okay. Which is going to so last time I stated this theorem about non-separated leaves being, so whenever you see branching in the leaf space, actually you get a whole bunch of extra structure. If I have 2 non-separated leaves, they're always related by some finite line of lozenges. A line is an arrangement like this, where they share opposite sides all going in a row. And if you orient everything this way, my non-separated leaves occur as the top leaves of some of these lozenges in the line. Okay. All right, so this is something you can prove out of the axioms, but I'm not going to do it because I don't want to spend half an hour. We did instead a kind of a baby theorem about fixed points giving lozenges that has some of the same tools last time. Okay. The lemma I need is also about lines of lozenges, and it's the following. So again, standing assumption is, suppose I have a plane with a group that acts Anosov-like on it. And I'm going to suppose that I have a line that's not just finitely many, but this continues on forever. So L1, L2, these are going to be my lozenges. It's an infinite line of lozenges. So here's my picture. I'm getting bad at drawing this. Okay. L1, L2, L3, L4, L5. I really just mean this kind of combinatorial arrangement in the line. And let's call, I don't know, let's call little li the leaf that's shared by big lozenge I and li plus 1. So this gives me, here's L1, here's leaf 2, here's little L3, etc. This gives me now an infinite sequence of leaves in the leaf space. Okay, that's the hypothesis. The conclusion is that this sequence of leaves does not escape to infinity. As I goes to infinity, this converges to something. And in fact, it converges to a collection of non-separated leaves, of course. Not one, not finitely many, but a bi-infinite collection of non-separated leaves. To a bi-infinite branching collection of leaves. What do I mean by bi-infinite? This lemma tells me that when I have non-separated leaves, they can be arranged in enumerated by some subset of the integers. Between any two, there's finitely many, and they're nicely ordered. So it makes sense to say, actually, I'm bi-infinite. I'm indexed by all the integers. So the picture is in my plane. These, if I squish my picture to make it realistically accumulate, it accumulates on something that looks like this, that goes in both directions. There you go. Okay. So again, out of some hypothesis on branching or structure, I get something extra something much stronger. And we're going to prove this just using kind of the axioms I have. And by prove, I mean I'm going to draw all the pictures you need to then go and like name things and write down the details on your own. Okay. So this proof has 2 steps. First, I have to show that this limits onto something. It doesn't escape to infinity. And second, I have to show that the thing it limits onto is actually a bi-infinite collection of leaves. Okay. So 1 limits to something. Step 1. So let's suppose for the absurd that it doesn't limit to anything. So if this sequence Li escapes all compact sets to infinity, what does that give me? That tells me that this line of lozenges, as I was drawing, right, goes on forever. It goes to infinity in the plane. And so in between the top and the bottom, I'm going to see a region that's trivially foliated. That's an unbounded strip in one direction, right? So I get an unbounded trivially foliated strip. Here, I'll draw a subset of it that's still an unbounded trivially foliated strip. So I get unbounded trivially foliated strip. Okay. I claim that. This is a fun exercise, and I'll give you enough hints to make it easy. Using axioms 1 and 2, this hyperbolicity everywhere, the existence of such a strip actually would imply that my whole plane was just the trivial plane. Okay. So we're going to use properties 1 and 2 from the definition to show that this implies that P is the trivial bifoliated plane. Okay. Why? Here's the picture proof. This strip, there's an open region of, say, like red leaves that pass through here of my red foliation. So one of them, by density of fixed points, is fixed by some non-trivial element of G. Actually, a dense subset of them are, right? The first axiom, hyperbolicity, tells me that G has a fixed point somewhere on this leaf. I don't know, could be in the region, could be out. I don't really care. Right. And up to switching G with G inverse, its dynamics look like this. So what happens when I apply the dynamics of G to this trivial foliated strip? I iterate G once, I get a bigger trivial foliated strip. Right? I'm pushing it both this way and up. Right? And I can repeat and I can repeat and I can repeat, and the limiting object, the union of all of these, is like a whole trivially foliated half plane. Right? Okay, great. That's already making it look pretty close to I'm the trivial plane, and the way you finish this argument is like, well, now consider a maximally trivially foliated region. If it wasn't the whole plane, you could find a leaf like this that fixed by some element that crosses the boundary and make it bigger. Okay. Okay, so that's the hint, and the rest of it is fill in what I said with a formal proof. There's no secrets beyond that. Okay. So, hint. You can always keep expanding. So that's the idea. Okay, great. So we know it does not, so this is a contradiction with the existence of like lozenges and perfect fits. This does not happen in the trivial plane. And, you know, because like that leaf doesn't intersect that leaf, so I'm not the trivial plane. So I know I don't escape to infinity. So I conclude that Li limits, it's a monotone sequence in the leaf space and it doesn't escape. So it limits to something, either a single leaf or a union of non-separated leaves. So let me tell you why it can't limit to a single leaf, and then you'll see this is also the proof why it can't limit to anything other than a bi-infinite collection. I'll draw this on my picture. So suppose somehow this limited to a single leaf. All right. The set of limits is invariant by some element of your group. Oh, wait, I need to go back to this theorem and remind ourselves that part of this was that there was a non-trivial element of my group that fixed this whole collection of leaves, everything that was drawn, fixed all the lozenges, and up to switching G with G inverse, its dynamics is like how I showed here. Right. This came from, this is some strengthening of axiom 3 that says that if I have a branching leaves, it's fixed by a non-trivial element of G. So there's someone who fixes, this leaf and then has a fixed point. And you can propagate this to say that G fixes all of these points. And then you have property 1 that tells you up to replacing with the inverse, you look like this. Great. Okay, so there's dynamics of G. Each Li is invariant by G. So since there's some G, so that G of Li equals Li for all I. This is theorem from last time asserted that such a G exists. This element G also preserves the limit. If there was just a single limit leaf, well, great, this single limit would be fixed by G. So by my first property there, G would have a unique fixed point on this leaf somewhere. And then it would act on it with hyperbolic looking dynamics up to switching to the inverse. It'll look like this. Okay, or maybe draw the arrows in the opposite direction. Okay, but this is already bad. Because what does that mean? I'm going to fix this leaf, this transverse leaf through it. Because I'm an accumulation point, this leaf is going to meet infinitely many of my Li's. Okay, and this is bad because the Li's already had fixed points of G up here and down here. And so I'm not allowed to have another G invariant leaf that hits them somewhere else that will contradict the unique fixed point and the hyperbolicity. So this type of behavior is not allowed. I'm doomed as soon as I have a fixed point. Okay. So was there a question there? So this argument also shows that G cannot fix or preserve, or equivalently by property 1 there, have a fixed point on any one leaf of the limit. Any leaf in the limit. Okay. It needs to shift it to some other leaf in the limit. All right. Otherwise, I have this bad behavior. Right. So let's erase the bad behavior and say what the good behavior is that I have some leaf in the limit, and G, the action of G, here I chose G versus G inverse, so it's pushing down. So G actually has to translate this along to another limit leaf. All right, and I can never run out because I'm not allowed to fix anything. And G inverse better translate it up. And so the set of limit leaves is infinite in each direction. So that implies I have a bi-infinite collection. And that's what we needed. questions? This lemma really isn't any sneaky tricks. It's just topology of foliations in the plane. Yeah?
Are you also claiming that there's infinite collection in form perfectly?
Ah, yes. So by theorem here, right, whenever I have a collection of non-separated leaves, if I take any two, then they're related by a line of lozenges. So citing this theorem, what does it tell me? Actually, it tells me I have more structure. Right? I started with something that looks like this. You know, that went on forever. It limits to a collection that looks like this. Apply that theorem. This collection actually comes from lozenges going in the other direction. So actually, there's another side of this region where I see infinite collection of things making perfect fits. Ooh, let's make one look actually like a lozenge. That's a little corner like this, and it goes on forever. And then I can do this. I can turn my head sideways and apply this lemma again and say, well, look at these sides of this infinite collection. Actually, the top, even though I only assumed it was going off in one direction, ends up going off in both because of lemma. And the bottom. And so what do I get is I get this giant trivially foliated, it's an open rectangle with a trivial foliation on the inside, bounded on all four sides by infinite unions of non-separated leaves. Okay. So this happens, this phenomenon, this is what Sergio calls a scalloped region. This is a thing you see already in early examples of bifoliated planes of orbit spaces that come from Anosov flows. The classic example of Bonatti and Langevin, its orbit space has this picture all over the place. And this lemma slash theorem is a way of saying this is actually a relatively common phenomenon. Question, yes?
Is that not a unique foliated, like how would you extend?
There's lots on this side. There's a whole half plane over here, which I haven't told you what to do yet. You can stick on anything. Yeah, it is an infinite region, but there's, yeah. Other question. Great. Okay, let's prove the theorem. Okay, so I'm going to erase this picture because it's not useful to you. Okay, so let's see, what order do I want to do this? We've been talking about lozenges a lot, so I'm going to first show, assuming some foliation has branching, I'm going to find two-sided branching in the other one, which is good enough to then go back to the first by the same argument and say there was really secretly two-sided branching there. And after that, I'll deal with the case that if there's no branching whatsoever anywhere in either of these, then we look like one of these two examples. Okay. So first step, I'm going to, step one, suppose, I'll relabel if you want, F plus has some branching. So what does that mean? I have some leaves, some pair of leaves that are not separated. All right. So by this theorem here, I don't know how many lozenges I'm going to get in a row. There might just be two, but I at least am going to see this picture. Some leaf L, some leaf L prime, a pair that is branching leaves, and theorem tells me there's going to be some lozenges structured like this. I don't have two-sided branching yet because I might just have this picture. Okay. So by theorem, I should have named this something. I don't know, theorem B for branching. I have at least two lozenges that share a side. Right? Maybe I have more because L prime was actually over here, but I have at least this. Okay. Okay. So what we want to do is find two-sided branching in F minus. So here I've color-coded this so that I guess F plus is the red foliation and F minus is the blue. Okay, so this picture so far is completely symmetric. So I'm just going to find branching. I'm going to transversely orient F minus this way, or orient its leaf space. They're transversely orient. And I'll find branching. I'll show that I have branching in this direction. Okay, and by symmetry, you could have just like put a mirror on this whole argument and find branching in the other direction too. Okay, so let's do this. I have some properties I'm allowed to use here. I'm going to use my hyperbolicity everywhere. Well, I'll use the everywhere part of it. And consider the open region of the leaf space of my minus foliation that consists of leaves passing through this lozenge. That's an open set. So property 2 says that somewhere in this open set, well, densely in the open set, there's a leaf that's fixed by some non-trivial element of my group. All right. So 2 gives me a leaf fixed by some non-trivial G and G passing, so this is a leaf of the minus foliation passing through that lozenge bounded by L. The one on the left. Okay, this is my picture. I'm going to use top, bottom, left, right to pick. We fixed an orientation after drawing it on the board, so I can say words like this. Okay. Okay. Axiom 1 says that this leaf has a fixed point somewhere. Let me consider a case first where the fixed point is, say, at the, what do I want to do first? That's not too hard. Above this picture. All right. So case, its unique fixed point X for G on, what should I call this leaf? Maybe L0. L0, here's X, a fixed point, is above the lozenges. Okay, great. I have another leaf that's fixed by G going through this fixed point. All right. And I'm going to consider, so there's L0, maybe I should call it L0 minus because it's in the minus foliation. And I'll call L0 plus the other leaf through X. Right. And let's consider the set of leaves that intersect both L0 plus and what did I call the top of that lozenge? L. So let's get a color that looks like blue. I have a set of leaves like this. There. It's bounded because L0 plus can't cross this perfect fit. So I can't have this collection of leaves escape to infinity and go nowhere. So it limits to something in the leaf space. Mm-hmm. This is bounded in the leaf space. I think I was using this notation last time. Limits to something. Here I'm taking a limit in my orientation, things that are on the right of L0 minus. So let's add this to the right of L0 minus. So it's bounded, so it limits to something. If its limit is not a unique leaf, well, then it contains some branching leaves, and I found the branching in the direction I wanted. Okay. Okay. So either a unique leaf or some branching leaves, and then I win. That's what I was hoping for. So if I haven't won yet, it limits to a unique leaf. What could this leaf possibly do? I claim the unique limit leaf has to be something that makes a perfect fit with L0 plus here. All right, so you need to argue a little, do a little drawing for yourself and think about topology of the plane for a minute to convince yourself that so the limiting object, the boundary of this, has to fail to intersect at least one of these. Okay, and the way things are configured, it's going to fail to intersect L0 plus, but almost intersect and satisfy the perfect fit condition. Okay. So in the unique case, I get a perfect fit. Okay, perfect fit tells me, last time we had a lemma that I actually proved that says if you have a perfect fit on some leaves and an element of the group, this was G, that fixes a point on this leaf, then actually you get a whole lozenge. This leaf also has a fixed point of G. You get a lozenge, so down at the end of this leaf, there's a perfect fit here also. And where can the lozenge fit? It's this leaf and that leaf need to intersect. Leaves don't cross, so they intersect somewhere down here. And I get another fixed point for my group element closer to the lozenge on the right. So I get a perfect fit. So from the theorem we proved last time, you also get a lozenge. And that other fixed point of G, well, that was the case 2 I was about to consider. Like, what if you have a fixed point of G that wasn't on top, but it was on the bottom? All right. So case 2, or the next step, we can keep going here if I haven't won yet. I have a fixed point. I don't know why, for G below these lozenges. And it's like the situation I was starting out in, but now I have a leaf that's fixed by G. I can forget what was there. I have this point here. And turns out you run exactly the same argument. You look at the other leaf fixed through here. You look at the leaves that simultaneously cross this one and L. Or I guess here I should use this bottom one. Call this other, I don't know, call this L prime prime. Run the same argument, and either you win, you get branching in the direction you want, or I find another lozenge. All right. So I ran the same argument. Win or lozenge. Right. Okay, so I can keep going. If I found a lozenge, ooh, I need more space in this picture. Let me draw a bigger version here. Whoop. Here's the schematic. What was the lozenge I found? I started with something like this. I found this little one here. I kept going. Either I win the game or I'm going to find another lozenge here going like this. or and then I can keep going. Now I have a fixed point above again. I can alternate. Either I'm going to win the game, or I'm going to find another lozenge like this, et cetera, et cetera. Right. They're all in a row. I repeat this argument. Either I'm going to go forever. Well, so either I've won, or I keep going forever, and I'm going to produce an infinite line of lozenges, conveniently, a case we studied in the lemma. With leaves L0, L1, if I keep going, L2, I think I was calling these minuses, L3, that stay in a bounded region. Okay. So if we don't win at some finite stage, if we don't find branching, we get infinite line of lozenges. But my lemma tells me that an infinite line of lozenges automatically gives me branching. So whatever this limited it to, I would have had some infinite branching in the direction I wanted it. I guess I can't branch there. I have to have a big leaf going through here. Okay. So in this case, lemma gives the branching we want. Okay. And you'll notice that I was careful with my bookkeeping. In all of these cases, I have a sequence going this way towards the right that limits onto a union of non-separated leaves. If you wanted to show branching in the other direction, you should start here and do the mirror image argument. That's what I needed for this part of the proof. I skipped a case. Okay, in the interest of time, you get this case as an exercise. What happens if I had a fixed point in the interior of here? How is that going to look? That's an easy case to treat that's fun to play with, so that's going to be your homework. This is the meat of the argument. All right. Okay, so case exceptional, L0 fixed point inside the lozenge. That's for you. All right. Okay. It's a mini course. It should have exercises, right? That's great. Okay. Good. Questions on what happened here? Okay. So this is Fenley's two-sided branching. And now what remains to prove this theorem is that if neither foliation has any branching, then it's one of these two pictures. So it remains to show no branching in F plus nor F mod. That's not grammatical, but you know what I mean. Implies trivial or diagonal strip. This diagonal strip is known as the skew plane, in case you hear that word at some point. Okay. Let's do this. Well, so the first observation is that if I have no branching, that means that the leaf space is a Hausdorff manifold. So it's a simply connected Hausdorff one manifold. How many of these are there? It's the real line. All right. So what we have is, i.e., I have that the leaf space of F plus and the leaf space of F minus are both homeomorphic to the real line. Okay. So in this case, this is nice. So a general thing, you can always, if you have a bifoliated plane, pairs of leaves intersect at a unique point. So you can always embed the plane into the product of the two leaf spaces. Well, here I'll write R cross R. But I mean the product of the two leaf spaces. Okay, by sending a point to the intersection to the coordinate leaf of the two leaves it's on. So I've already got my plane as a subset of the plane, and I need to show that it's either the whole plane, the whole R2 trivially foliated. This comes with its standard product foliation, right? And I want to show it's either the whole R2 or it's something that's isomorphic to this diagonal strip. Okay. All right. So for this, I need more space. Don't need any of this anymore. So here's a nice way of thinking about it that I first read in work of Barbot, but perhaps was done earlier, I don't know, is you can actually think about this as being bounded, this region as being cut out, like bounded between the graphs of functions. So let's consider the functions that go from the leaf space of, say, the first foliation, the +1, to the leaf space of the minus foliation. Well, I'm going to take, I'm thinking of this as R, but I'm going to take supremums as infinity and infimums, so I'm going to add also plus and minus infinity. Okay. And what is this function? I take a leaf, and I'm going to send it to the supremum of the set of leaves. These are parameterized now by numbers. My leaf space is R. So L minus in a leaf of F minus that intersects L plus. So they do intersect. Okay. So if this is infinity, it intersects an unbounded upwards set of leaves of the minus foliation. Okay. I have another function, maybe this is S for sup. And I have another function I for inf, which is the infimum of this set. Right? So these are really functions. If I make this identification, they're functions from R to R union plus minus infinity. And under this recipe, my plane is really isomorphic to a chunk of R2 that's bounded above and below by these two functions. Right? So by the graphs of these functions. Graphs of S and I bound the image of P in R cross R with its trivial foliation. Okay? So this instruction puts my bifoliated plane in a foliation-preserving way inside of the vertical horizontal foliated R2. Either is maybe the whole thing, maybe these are like both, it's like constant infinity and minus infinity, or I have, some possibly discontinuous, I don't know, graphs of functions, and the region I see is in between these. And this is what my plane looks like. All right. Great. Okay. Well, I want to prove it doesn't actually look like this, because that's not the diagonal strip. So let's think about some properties of these functions. So the first thing to note is that if the sup function has a local minimum anywhere, this will give me branching in the L minus leaf space. Okay, here's the proof by picture. I have a sequence of leaves going upwards in the L minus leaf space that limit to two different leaves. This happens whenever you have a local minimum, even if that's like a flat point or something like this. Okay. No local minima, similarly no local maxima of the inf function. I also can't have any flat points thanks to hyperbolicity. So let me do this argument. If at some point I had a non-infinite, or if I had some plateau in the graph of this function, All right. So here's now what my plane is supposed to be looking like. I don't know, that's just a little piece of the top of it. Hyperbolicity everywhere tells me I have some leaf fixed by a non-trivial element of G that meets this plateau part in the supremum graph. And the dynamics tells me, well, that this leaf fixed by some non-trivial element of G, given to me by property 2, has a fixed point on it. So there's another fixed leaf through here, and my dynamics up to switching G with G inverse is contracting, expanding in this direction. And so as I iterate, whatever this plateau was is going to have to get bigger. Right? Okay, so to formalize this, you need to quantify, like consider a maximum plateau if it's not the whole thing, find something near the edge that intersects it, and I have hyperbolic dynamics. I could have made it bigger that contradicts maximality of this plateau and contradiction. Right. So this argument shows that if it's locally constant, or if it's constant somewhere, if constant on an open set, then globally constant everywhere. It's just constant. All right, thanks to hyperbolicity everywhere. All right. Okay, so this was giving me a monotonicity. This is giving me strict monotonicity, or else I'm just completely constant. So I'm looking like the top of the trivial plane. And what do we conclude? I ran out of time, basically. So, but I think we're now at the part where you're like, oh yeah, I believe that. All right. So exactly this kind of argument tells you that sup and inf are both either constant, they're both constant, that would give you the trivial plane, something isomorphic to the trivial plane. Okay, and it ends up they have to be infinity, otherwise I'd get this open strip which just looks like the infinite plane, so everyone intersects everyone, so I guess they were infinity as we thought. Or both strictly monotone. Okay, from which you should make a short argument using what shape is a lozenge to say that they're monotone, increasing or decreasing both. And you get a picture like this, which it might be a little wiggly, but if you change your coordinates slightly, you still get the skew picture exactly. All right. So exercise, a region bounded by the graph of two strictly monotone increasing functions is isomorphic as homeomorphic as a bifoliated space to that bounded by the graph of two linear functions with constant slope. Okay. That was a little rushed at the end, but I will end now in the interest of not stealing the rest of your time. I hope this was a nice taste of how from some basic axioms, which I just erased so you can't question them too much, you can recover a lot of in fact, classic theory of what we know about Anosov flows and the associated structures of their foliations. Thank you.
Questions for Katie?
Can I ask a question from far away?
Yes. Hi, Steve.
Hi. So you get strips, planes, and trees, is what I see from far away. So is there a quasi-isomorphic classification? If you look at these spaces you're getting and you break the Anosov flows into these types, one of them is torus suspension, one of them is pseudo, it looks like you get a lot of structure on your tree at infinity.
So here's it. So if the leaf space is if the orbit space is the trivial plane, then from way back, even like following from work of Planck and just sort of understanding this, you can conclude that you were a suspension flow. Okay. If the leaf space is this strip, then many flows are possible. Like there's vast. In fact, so if you take here's one for people in the audience. If the Rabe flow of a context structure happens to be Anosov, where it often is, you always get this strip picture. All right, so there are many diverse cases where you get the strip, and then somehow, I don't know, maybe there's even more, whatever that means, where you get very complicated looking foliations with two-sided branching in each, and even a classification of what all of these look like we do not have. So have we classified flows? No. Have we classified orbit spaces? Like also no. Lots of rich things to study here. Yeah.
Thank you.
But we will. That's maybe.
It's a 500-mile race.
Maybe ask a quick question. Is there any kind of realization theorem given the conjugacy classes of periodic orbits you can build Anosov flow with those?
No, great question. Okay, yeah, so here's more of a thing. You fix a 3-manifold that you like, and maybe you know it has at least one Anosov flow on it or something. Like, what subsets of, free homotopy classes, of like conjugacy classes in pi1 arise as orbits of, as closed orbits of various flows? Like, what types of things are possible? I think that's a super interesting question, and I do not know the answer. Yeah, I can maybe say, some things that have to happen, and I don't know, if you have some very strong things, you might get another thing, but like, I don't have a general answer to that question, and I think it's very interesting.
Well, if there is no more question, let's thank Katie for wonderful talks.